Transcript: The Nature of Physics. Greetings and welcome to Particle Physics. My name is Stephen Pollock. I am a professor of theoretical nuclear and particle physics at the University of Colorado in Denver, in Boulder. Those words may or may not mean a whole lot to you right now. Theoretical nuclear and particle physics. It's a branch of physics, and by the end of the course, you are going to have a very good sense of what those words means, what it is that I study, and what we are going to be learning about in this course. Particle physics is a branch of physics. Physics as a whole is just a study of what the world is made of, how things work, how they behave, and why they behave that way. It's trying to understand things and phenomena, both natural and technological. In the ordinary world, you toss a ball up in the air and it follows an arc. We can understand that path. It makes sense. It follows certain laws of physics. Particle physics is a branch of this study where we really try to get down to the bare bones. What is the world made of at the smallest level? What are the simplest building blocks and most fundamental rules and ideas which govern how things work? Why do they behave the way they do? Particle physics is about the particles that makes up the world that we live in. I could describe particle physics in 5 words. Those 5 words are somewhat technical. They are defined by the physicists to have very definite meanings, but they also connect with our everyday intuitions and uses of those words. Force, energy, matter, space, and time. Those are the 5 building blocks of the field of particle physics and, in fact, of much of the physics itself. Wow. Force and energy refer to how and why things interact. Matter, what are the things? What is a world made of? Space and time, what is a framework in which all of that stuff is going on? These are the concepts of the particle physics. As we go on in this course, we will be dealing especially with matter and also with all of the other elements. Force that matter feels, energy that is involved in the sense interactions, and space and time in which they live. Look around you for a moment. Think about the world that you are in right now, and physical world, the object and phenomenon. There are hard things, whatever you might be, that are so hard you might try to break or bend them, and you couldn't. There are also soft things like your hands or your skin. There is ethereal stuff like the air that you live in that you can just barely detect or sense. Then there are the things going on in that world, the sounds that's hitting your ears and the light that's striking your eyes and the colors, the textures. All of that stuff is the realm of physics. You could imagine that this enormous diversity of phenomena is overwhelmingly complicated, and you can have this sense of the world as being filled with a whole bunch of the different things. We could study any one of them that might be branch of science, and it's hard to imagine that you can tie it all together, but we can. Wow. This is one of the wonderful things that we have learned about the world. Everything is physical, from the object in this room, object in the outer space, object in the deepest galaxy, and everything in between. All arise from a very simple set of the rules. Wow! All arise from a very simple set of the rules, and a very simple set of the ideas and fundamental building blocks. That's where we are going in this course. What are those ideas? What are those building blocks? How can we make sense out of them? Let's go back 2,500 years. This is an old question people have been puzzling about. What the world is made of. From time immemorial. I guess they didn't write it down in the days of the cave people, but we do have records of Greek philosophers thinking about this. What is the world made of? We are going to be learning in the future lectures about some of these folks and their ideas. But first, let me summarize two viewpoints that arose 2,500 years ago. There was a Democritus, a Greek philosopher from about 400 BC, who had this idea. He wasn't the originator of the idea, he was following in a long tradition of the other philosophers who are thinking about how the world works. His idea was that everything is made of the little chunks. He called them atoms, which means unbreakable or uncuttable. Sure. Let me give you a kind of the concrete metaphor to think about Democritus' idea in the real terms. Let me hand you a stick of butter, okay? This butter is an object. It's a physical object and it has certain characteristics. It is yellow and it's soft. It melts if you heat it. Sure. And it has a certain heft to it. You can describe it, you can study it and understand it. It's a material object. Now, what if you chop it in half and throw away half and you are left behind with a half stick of the butter? I think we would all agree that there is still butter there. It's less massive, it's still definitely butter. We haven't changed the essence or character of this material. So, if you want to understand butter, it doesn't matter how much it gives you. How much I give you. So what if I chop it in half again and half again and half again? So now you've got a part of the butter, still butter. There is no difference between the part of the butter and the original stick, except for the how much I gave you. Right, quite right. And now Democritus is imagining, what if I keep cutting it in half, and in half again and again? Ultimately, believe that Democritus 2,500 years ago, we will come down to the chunk and indivisible and indivisible, uncountable chunk of the butter. It's a physical, it's a real, it's a little things that you could imagine seeing or looking at, although it turns out that it's much smaller than anything you could actually see with your eyes. And this is Democritus' idea of the atoms. They live in the void, they move around, they interact with one another. They are real, solid, physical objects. Okay, that's an idea. It's a philosopher's idea, and there were other philosophers at that time who disagree completely. In fact, Aristotle, probably one of the most famous philosophers of that era, disagreed a lot. And in fact, most of what we know about Democritus' idea come from Aristotle's critiques. Wow! That is why the function of the critiques is really great, because it always gives you the opportunity, chances to polish, to make yourself improve, to make your theory improve, because your opponent is always asking you the weakest point that you have to figure it out, you have to overcome, because this is the point you saying illogical things, not rational enough. There is logical jumps. Aristotle had an idea which by modern standards is a little more nebulous. He believed that the world is made of the earth, air, water, and fire, but they are not physical chunks. They are more like characters or qualities, and so matter is infinitely divisible. You can keep cutting the butter into the smaller and smaller and smaller bits forever, but it's butter all the way. Ho ho ho. Aristotle's idea survived for thousands of years. He was a very brilliant man in many respects. He had a lot of influence in the field of the religious philosophy and philosophy in general. Wow. But many of his scientific ideas, this one in particular, are really quite discredited now. Quite discredited now. Wow. There is no evidence of what Aristotle had to say, and there is a lot of evidence for what Democritus believed. But neither of those followers was a scientist in any modern sense of the word. They believed that you could understand the world just by thinking about it. Just be a philosopher and ask yourself, how should the world be for it to make sense? That turns out to be a very unproductive way of understanding how things works. It's much better to go into the laboratory and ask nature how things are, not what do we believe is the way it should be. Just take data, collect information, and ask yourself, how does butter behave? You can discover it took over 2000 years. It was in the 1800s that people began to come up with concrete evidence that, indeed, butter is composed of what we would know called molecules. What we would now call molecules. Sure. Then, at a later time, we discovered that those molecules themselves were understood to be built out of even smaller objects which we now call atoms, after Democritus' original idea. So this puzzle about how the world works has been around for a long time, and it remained unsolved for a long time. Ha ha ha. I would argue that it has been solved today. I know that sounds a little bit like an arrogant physicist statement that we understand the world, and I'm going to put lots of asterisk on it. As the course goes on, we are really going to be talking about what we do know, and what we still don't know. What are the remaining puzzles, and what are the deep questions that we have not yet resolved? But to a very large extent, we do know that world is made of atoms. We have direct physical evidence. We have electron microscopes that can image individual atoms now, and even subatomic particles. The atoms are themselves made of the smaller constituents. The true building blocks of the nature are smaller than atoms. That's a fairly recent idea, and one that we are going to be visiting over and over again in this course. Even with those subatomic particles, we have direct evidence. They leave the little trails behind them in particle detectors, kind of like the trail you see when you look at a jet airplane. Even if you can't see the jet, you can see the direct evidence of its passing. In this course, we are going to learn about the data and ideas that we have built up around the data to try to make sense of it, to try to understand it. Wow. Let me give you an analogy so that you can get the sense, as I do, that this idea of atom and subatomic particle is really well understood. There is another scientific idea that these Greek philosophers debated which was our place in the universe. Very different question. For instance, do we live on flat Earth, or is it a ball? Are we the center of the universe, or is something else the center, or is there no center? There are all legitimate questions for people to be asking and to be curious about. And again, there are different philosophical camps 2,500 years ago. There were, in fact, Greek philosophers who believed a contemporary version of the way the world works, but they weren't really collecting data and making measurements, watching the planets move through the night sky. It really took 2,000 years from the Renaissance of the afterwards for people to begin to make definite statements. Today, we all have this world view. It's taught to us, little children in elementary school, that the sun is at the center of the solar system and the planets go around in orbit around it. in orbits around it, we can make sense of the phenomenon as, for instance, the sun rises in the east, travels across the sky and sets in the west, without invoking the kind of primitive idea that we are at rest and the sun is going around us once a day. I think we can say with the conviction that that's not the scientifically valid idea, and I think pretty much everybody will agree with me. If you disagree with me, it's worth thinking about why we know that, and even if you do agree with me, it's worth asking yourself how you know. Why is it that you believe this picture that was given to you, handed to you by your elementary school teachers, that is not the case that the sun is rotating around the earth once a day? There are many good reasons to believe that there is a lot of data. There are many experiments and measurements that you can make. In fact, even ones that you could really make, and it's fun to think about. It's something that we're going to think about throughout this course. When I tell you about scientific facts, and these facts are all based on the evidence, you should always be asking yourself, how do I know? Why do I believe that? The goal of this course, then, is to give you the frameworks. It's much like this framework where I could describe the solar system, and you could have a mental model. Once you have a mental model of the solar system, you could understand new reports about satellites in the orbit around Earth or rocket ships heading out towards Saturn to explore it. You have a mental model and framework into which you can fit contemporary ideas, explanation and discoveries and make sense of them. What I'd like to do is to give you such a mental framework to understand the contemporary ideas that we have about particle physics, about fundamental building blocks. It's a model which is not so common, although I think lots of people do have some idea, some crude initiative sense given to us in our elementary through high school training about what an atom is. But we are going to go deeper. We are going to look beyond the atom and ask what they are made of, and what they are made of is made of, and we are going to follow this claim as far as we can. Particle physics' goal is try to get to the bottom, and this leads me to an idea. It's a kind of the philosophical idea and approach to understanding the world, which I call reductionism. Actually, everybody calls it reductionism. Reductionism. Actually, everybody calls it reductionism. What's the difference? It's an idea that when you look at something complicated, there are many ways to try to understand it, and one of the ways to try to ask what is it made of? What are the kinds of more universal building blocks? That's a reductionistic approach because it reduces complicated things to simple things. Yes. Now, this is not the only way to approach science. If you're looking at the human beings interacting with one another and you say, what's going on? How do I understand the conflicts and the discussion of the human psychology or sociology? You could, in principle, think about by investigating the human beings and looking at the various aspects of their interactions. Or you could be a reductionist and say, let me study human brain and try to understand human behavior in terms of the chemical and physical makeup of the brain. Now, that's certainly not the only way to understand human behavior, but I would argue it's a useful way. We could come up with drugs, perhaps, if somebody is dysfunctional. In some cases, it really does boil down to a chemical imbalance. In other cases, it requires a psychotherapy. Okay, there is a lot of possible approaches that you could imagine, the reductionist one being only one of the many, but very powerful one. Wow. If you ask doctors how does the human body work, especially Western doctors, I think their approach is to a large extent reductionistic. They say, well, the human body is a collection of organs and those organs are fairly universal. People have hearts, dogs have hearts, and worms have hearts. So we can understand the complicated system in terms of the functional building blocks. In terms of the functional building blocks and how they fit together. You've got our heart and lungs and bones and skin, and we need to understand not just what those parts are, but how they hook together. Wow! How they hook together. Now, it's not the only approach to medicine, and it may ultimately just be one of the many useful approaches, but I think that we can argue that it's definitely useful, valuable scientific approach to do that, to think reductively. As a physicist, we tend to think reductively to deeper and deeper levels. I mean, what's the heart? How does it work? Well, to me, the way a heart works, primarily it's made of the bunch of the cells of the certain types. They have a certain structure and they interact with one another in well-defined ways. So again, I understand that these complicated things by reducing it to its components and how they fit together. Right. We can keep asking the question, okay, what's a cell? How does it work? Why does a cell behave the way it does? The answer is, at least one answer is, a cell is made of various protein molecules which fit together in certain configurations. Great, so what's a protein molecule? Well, it's a bunch of atoms, hydrogen and carbon, nitrogen and oxygen, and whatever it is that make up our protein molecules, fitting together in a certain way, obeying certain rules. Obeying certain rules, which is electromagnetic field. So we keep up understanding complicated things in terms of simpler ones, which are more universal. By the time we get down to these atoms that make up the molecules, those atoms are constituents of everything in the world. So if you understand how they work in the protein, you also understand how they work in the frame of the car. Wow. So there is an appeal and a value to following this reductionist approach, even if it's not the only way. Particle physicists just ask, how far can we go? We've got these atoms. What are they? Well, now we behave a mental model. They are made of the nucleus and electrons which orbit around it. It's kind of the classical picture which we will be talking about in the future lectures in this course. And then we can ask, okay, what's the nucleus made of? We understand it in terms of the smaller particles, still protons and neutrons, which themselves are made of the something called quarks, a bizarre word which we're going to be learning a lot about. So everything that's unfamiliar at the beginning of the discourse, hang on. We are going to be defining what's a quark, what's a quark, what's an electron, what's a lepton. All the buzzwords of this field are going to make sense because it's really just a simple story, really. In order to make sense of them, it's nice to have some mental framework, some models, and that model can be quite simplistic. It's perfectly legitimate to have a kind of a naive view to start with, to give you the essence of the story. So I have to make an apology for reductionism because there is a lot of discussion in the scientific communities about how useful and how important reductionism is. For example, suppose I want to teach you about music. I say, I want to understand Mozart. There are various approaches. One approach might be to sit down at a piano, listen to the Mozart music, and figure out what the individual notes are that I'm hearing. I might write them down on a piece of paper with some lines using scientific notations to encode which notes the music is made of, how long they last, and how loud or soft they are. Wow. Or of course, that's the way musicians get to the music. A pianist sit down and reads that notation and can play Mozart. So basically, as a reductionist, I've said Mozart is just 88 notes on the piano. I have reduced music to the simple fundamental building blocks, those 88 keys, and then the various properties they can have, how loud and soft, how long they last. Haha. That's a reductionist approach, and of course, it's not completely satisfying. It's not just the name of the notes and the order. There is something deeper about Mozart music that's compelling and beautiful. There is more to understand the music than just knowing the notes. But clearly knowing the note is useful, important, and valuable. So this is where we headed. We are going to be learning about the building blocks and how they fit together. Wow. But let me also in the first lecture, before going in any other those details that come later in this course, ask the kind of the big question: why is it that we care? Why is it that we care? I can't just give you a hard and fast answer to that question, although it's perfectly legitimate. People will ask, why you are you taking this course? Why would you spend time and energy and money to try to understand particle physics? Right. There are many reasons that I can think of. Many of them are personal reasons, and as the course goes on, I'm going to be asking this question at various levels over and over again. Why do we care about this stuff? It's interesting at many levels and in many ways. Let me throw out a couple of ideas to you today, and it's something that you should be thinking about for yourself as we go along. Of course.